Hello, this is Robert, and in this video I would like to discuss creating just the right size for a C-string, a dynamic C-string. And then we'll be discussing the destructor a little bit later. But for now, let's focus on how we can create a dynamic C-string that is just the right size. I set up a struct and a class just to demonstrate, and so I have a struct called list struct, and then I have a class called list. Also notice that there is a difference in the way that we are creating our list struct array right here. The asterisk means that this is an array of pointers. So we have an array of list struct pointers, and it's called the list. Okay, so let's take a look at our constructor, and right now it just has count equals 0, so that's all we needed to do. When our list is instantiated, the first thing that's going to happen is that count will be set to 0. So that will mean that we have an empty list. My list is declared in the main function right here, and so when execution reaches this line, the constructor is invoked, and we have this default constructor right there. Okay, notice in the public section of my class I also have a prototype here for add item. Okay, and I've created the beginnings of add item right here. So basically what we need is we need a temporary C-string to hold the user's input. We don't know how long the list item is going to be until the user types it. So we're just going to set up a temporary string that is a particular size, long enough to hold any item. So 256 characters ought to be enough to hold any item. And then we need to write the code to actually store the item in temp into the list. Okay, so we now know what the user wants to add to the list. The way this array of pointers works, it's just a set of pointers right now. We haven't actually allocated any memory for these structs, right? So this is an array of struct pointers, and so we will have an array of these when we instantiate them. Okay, so we have an array of pointers, and so in order to add anything to the list, we have to allocate the memory for one of these. All right, so let's go ahead and fill in the code to create a list struct item to create it in memory. Okay, so what we need to do is we need to use count. So count is keeping track of our current item. And so what we need to do is we need to say the list at count, right? So we're accessing that pointer at location 0 because this is the very first one, equals new list struct. Okay, so list struct right there. So now I have a dynamically allocated list struct. So now that I've created the list struct, I need to allocate the memory for the list item. So that is a char pointer, right? So we're going to be copying temp into the list item. So we asked the user to tell us what they would like to add to the list, and then we did cin.getLine. So temp is already loaded up with whatever the user wants to add to the list. Okay, and now we have a new list struct at location 0. So now let's allocate the memory for the C string inside of our brand new list struct. Okay, so what we would do is we would say the list at count, and then normally we would use dot notation, right? And so we would say something like the list, like that. It turns out we can't use dot notation anymore because this thing is a pointer. So what we have to do if we want to get access to the list is we have to dereference this thing. All right, so we can use the dereference arrow for that, like that. Okay, so the list at count, oops, I put the list. I actually want list item equals new char. Okay, so here's where we need to find out just exactly how many characters to allocate for our list item. Well, we know how many characters are there if we use stringlen. Okay, so what we can do is we can say new char, and then we can use the square brackets to specify how many we want. So that would be stringlen of temp plus 1. And we'll explain why we need that plus 1. Okay, so let's suppose that this is a grocery list. And so let's say that the user wants to add milk to the list. Okay, so we have 1, 2, 3, 4 characters in milk, but we need one additional character for the null terminator, because remember that all C strings are null terminated. So I'll just put a 0 right there, or if we wanted to represent it as a char, we could use single quote escape 0, right? So now we have 5 characters that we need to have memory allocated for, right? 4 for the letters and 1 for the null terminator. So when we do stringlen on temp, we're going to get 4, and then we add 1 for the null terminator. Okay. After we have allocated our new character array, we can go ahead and copy temp into the list item. Okay, we know exactly how many characters are inside of temp, and we know exactly how many characters were set aside for list item. So it is safe to do string copy. Normally we would use string n copy and specify the size. But since we allocated just the right amount of memory, that's not necessary. We can just do string copy. And notice that we have the destination that goes first. So the list at count. And then we dereference it to get to list item. And then we have our source, which is temp. Okay, so now we have copied temp into our brand new list item that we just allocated. What we need to do next is increment count, because otherwise, if we don't increment it, then the new item that the user wants to add to the list will be copied over the top of location 0. We want the next item to go into location 1, right? So we say count plus plus, like that. We're almost done with add item here, but there's one more thing we should do. Remember that we have a list of pointers right here, and that is array size. So it's still possible that we could run out of memory because this array is a specific size. So let's put a check in here at the beginning to find out if count is equal to array size, greater than or equal to array size. So if count is greater than or equal to array size, then we should return from the function right away. But let's go ahead and say what happened. So sorry, no more room in the array. And then can't add new data. Okay, so that's a good explanation for the user. And then we can just go ahead and return from the function right there. Okay, so that is how we can set aside just the right amount of memory for a C string. In just a minute, we will go ahead and take a look at how we can deallocate the memory that we've allocated. Remember that we would have a memory leak if we don't deallocate the memory or delete the memory. So let's take a look at a couple of options in just a minute. So basically what we need to do is create a destructor. So we'll create a destructor in just a minute. Okay, this is part 2 of our video on how to create dynamic C strings of just the right size. So we covered add item, and we allocated just the right amount of memory for a brand new C string, a dynamic C string, inside of our struct, which was also dynamically allocated. Okay, so if we take a look at main right now, we've declared our list object, and then we've called add item so that they can add an item to the list. And then after that, we're going to just be returning from main. Okay, and so when we reach the closing curly brace of main, myList is going to go out of scope. And so when myList goes out of scope, it will be removed from memory because the program is terminating. But myList contains some dynamic memory. And so when myList goes out of scope, if we don't deallocate that memory, then we will have a memory leak. Alright, so what we need to do is we need to modify the destructor so that the last thing that happens when myList goes out of scope is the destructor is invoked and we can deallocate the memory there. Okay, so I've added the destructor prototype to the list class, and then I've decided to create the list destructor right here. Okay, so we potentially created several of these items, and when we created a brand new item, we incremented count, right? So we know how many items are in the list because of count. So what we need to do is we need to loop through our list struct pointer array, and we need to deallocate both the list item and the struct itself. Okay, so this thing is dynamically allocated, and also this thing, right? So we have a dynamically allocated C string inside of a dynamically allocated struct. Okay, so one way to handle this situation is to create a loop and loop through the items in our list. Okay, so for int I equals 0, I is less than count, I plus plus. Okay, so this will allow us to loop through each struct, each dynamic struct that we have allocated. Okay, we can't deallocate the struct until we have deallocated the C string. Okay, so we have to deallocate the thing inside of the struct before we deallocate the struct itself. Okay, so what we're going to do is we're going to use I to get access to each list item. Okay, so we need the list, and then we need count, or I'm sorry, I. Then we need to dereference that to get to the list item. Okay, so that is the list item. This is the thing that we need to delete. This is an allocated array, so the version that we need is the delete for arrays, which has square brackets at the end. So now we are deleting the list item char array or C string. Well, after we have deleted list item, now we can go ahead and delete this thing, right? So this is a struct, and it is just one struct. So for that, we will be using the version of delete that just deletes one item, so no square brackets. And then we say the list at I. Okay, so this is how we can deallocate the memory for the items that we have dynamically allocated. There's one additional thing that we should do just to be on the safe side. This is pretty much a very simple program, so there's really not much of a chance that we could be deleting memory that we've already deleted. If we try to delete memory that has already been deleted, then we will have a segmentation fault or some other kind of a crash. So it's always a good idea to check and see whether or not memory has been deallocated already. So what we should do is we should say if the list at I and then list item, if that thing is not equal to either null, depending on the age of your compiler. So if it's pre C++ 11, you should use null, or you could use null pointer if it is C++ 11 compliant. Okay, so this will allow us to find out if it has been allocated. So this is asking, is list item actually pointing to some memory address? And if the answer is yes, then it's safe to go ahead and delete it. This will only become false, though, if it's not equal to the null pointer. So the next time, if we accidentally try to delete this memory one more time, then we need this to be false. So, long story short, we just need to set the list at I list item equal to the null pointer. Okay, so there we go. Now if we try to delete it somewhere else in our code, there's no chance that we could try to delete this memory twice, because the next time, if we make a mistake and try to delete it twice, it will be equal to the null pointer, and we will skip the next time we try to delete it. We should do the same thing with the actual struct. So let's go ahead and check and see if the list at I is not equal to null. Null pointer, since this is C++ 11. We will delete the list at I, and then we will set the list at I equal to null pointer. Okay, so this is one way to handle deleting the dynamic memory that you have created. Notice that we are deleting the C string, and we are deleting the actual struct. One other option that we could do is we could actually place this code inside of a destructor for our struct, and so we could actually push it down a little bit. When we call delete for dynamically allocated memory, that also calls the destructor for the item that we're deleting. In this case, it's a struct. So if we wanted to, we could create a destructor for the struct, and then we could add this code to the destructor for the struct. It might make the code a little bit easier to understand if we do that. So I'm going to go ahead and cut this out of our destructor. And now you can see that we're just dealing with the structs in the list. So we're going to be deleting those. Okay, if we push the destructor down into the struct to delete the C strings, we need to create a prototype for the destructor in our struct, the list struct right here. So let's go ahead and add a destructor for our struct. So list struct, and I put the tilde in front of it to specify that this will be a destructor. Okay, let's just go ahead and put it right after the struct. It's as good a place as any. And so what we can do is we can say list struct, and then the scope resolution operator, and then we have the destructor. So we need the tilde right there, so list struct. And then we can just put our code for deleting the C string right in here, but we don't need a loop for this one, right? Because when we are deleting the struct right here, when we call delete on this particular dynamically allocated struct, this will invoke the destructor for each individual struct. So all we need to do is say if list item is not equal to null pointer. So now that we're inside of the struct itself, we don't need to dereference the list at I, so we can just say list item, and if it's not equal to the null pointer, we'll just delete the list item, and then we'll set list item equal to the null pointer. So there's a couple of ways of dealing with deallocating memory. In this version, we created a destructor for the struct itself so that the struct is responsible for deallocating its own items. And then the class just has to call delete for each dynamically allocated struct. Both ways are fine. You can choose the way that you would like to deallocate the memory. But you do have to deallocate the memory somehow. Okay, that about does it for dynamically allocated C strings and creating destructors to free dynamically allocated memory.